Hello, everyone. It's my pleasure to speak here today. I would like to thank the organizers. I would also like to thank Matthias Socken from Microsoft, who sponsored our venue here today. And I would like to thank all of you for being here during the lunch break, listening to the talks. Never enough. So thanks to you for being here. I'm mie Guillaud. I'm in charge of the theoretical research team at Alice & Bob. And I have one goal for this talk is to give you a bit a high-level understanding of our technology. What are Qubits? Why do you think it's important? And I will try to clarify what I mean by hardware-efficient quantum computing with Qubits. So I don't think all of you know Alice & Bob, so I'll just give you a couple of numbers. It's a French quantum hardware startup based in Paris. It was founded 2 years and a half, almost 3 years ago, actually, now. And we're about 60 people. So where are we on the ecosystem? So you can see the little cats there. We're focusing on chip design. So we're a hardware player, but not full stack, really focusing on building, focusing on where we think we have the most impact, so really building the hardware. So usually I motivate a bit before I get into our technology, I motivate a bit with why do we need this technology? But I'll go quite quickly through this part because we've been hearing this over and over again for the past 2 days now. So a bit of background. Where we are now, I think we are leaving this quantum supremacy experiment regime in the left. So we've seen in the past 3 years a couple of groups. So first by Google and then by Zhang Wenpeng in China, also followed by Xanadu on different platforms, doing these supremacy experiments where they're able to do a computation or solve a problem with a quantum hardware that is impossible to solve with a classical hardware. However, these problems are not really, there are no known applications for this problem yet. So it's not really a business advantage. And right now we're entering this so-called NISQ era that John Preskill mentioned this morning, where you can really start to have some applications creating value. And the reason why we got there is really because of these reduction of error rates. So the numbers I'm putting in this slide comes from the BCG analysis, where they show there is a direct connection between the error rate that you can achieve and the value that you create. So I've put a couple of players there in this NISQ era that actually focus on scaling the machine first, so trying to get to a number of qubits where you can really have applications that are useful and both classically non-trivial to solve. And then at the very far end, you have the large-scale quantum computation regime, where you need error rates that are so low that you will most likely require error correction, unless you have a change of paradigm, a new technology that's created. And this is really there. People think that the most value will be created. So Alice & Bob is falling into this last category, and I will explain a bit more why. So since the beginning of this conference, we've heard a lot that we need that we need error rates that are extremely low to actually tackle the most difficult problems. I'll just give you a quick tour of the literature to motivate why. So for instance, in chemistry, where we think there is an advantage, there is this paper by the Microsoft research team where they show what does it take to have really a chemistry advantage using a quantum computer. So here is the algorithm that they propose where if you want to basically solve the problem of finding how a nitrogen protein behaves in a complex chemical environment, you can have an advantage by using a quantum computer on a subroutine. But the numbers that you see on the right here are the number of gates and the time that it takes to solve this problem. So if you zoom in, you see, for instance, that for a specific problem, you need about 100 to 1,000 of perfect qubits, and the circuit depth is about 10 to the 14 gates. That means basically that if you want to be able to have the output of the algorithm that is not completely randomized by the noise, you need an error rate that's about 10 to the minus 15. So that's why you need so low error rates. It's actually not so much the number of qubits, it's really more the depth of the circuits. You have a bit the same example in financial optimization, for instance, where the team at Goldman Sachs did the same exercise of really compiling the problems on a perfect quantum computer to see what would be the number of qubits and what would be the depth. And here they also find that they need error rates of 10 to the minus 13. And also, it's the same in, for instance, cryptography, where if you really want to use short algorithm at scale, so on integers with a large number of bits, then you need about 10,000 perfect qubits and 10 to the 11 quantum gates. Now, of course, all of you know that these error rates are within the reach of a classical hardware, where you have typically an error rate of 10 to the minus 25. But this is way beyond the best processors that we have today, among which, for instance, the Sycamore chip by Google, where you have 3 to 4 nines of gate fidelity. So we've heard that, so I'll keep going quite quickly because all of you are experts of that, but you know the answer is quantum error correction. And there, just to give you a taste of how it works, the idea is really that you will delocalize the information in some sense, because the way errors are created, I mean, physics is fundamentally local. So here, for instance, if you're able to build a 2D array of qubits and encode in an entangled degree of freedom of this array the quantum information, then there is no way for the environment to probe what is the state that you have encoded, and hence it gives you protection. So it's what John Preskill calls fighting entanglement with entanglement, typically. The drawback of that is that you have a physical overhead, meaning, you know, now one qubit is basically this whole array of physical qubits. So you've seen that the size of the machine really increases by just implementing error correction. So you can look at it this way. You have a threshold for error correction where increasing the number of physical qubits you use per logical qubit gives you access to lower error rate. But as a consequence, you know, given, so on the right-hand side graph, given that you are one order of magnitude below the threshold, if you want to achieve a logical error rate of 10 to the minus 10, say, you need about 1,000 physical qubits per logical qubit. So you can, again, in the literature, people have looked at, okay, if we take into account this, this overhead, what is the size of the machine that we need now? And we've had a very nice talk by and a demo by the Microsoft Quantum team yesterday, and I've put up this, this paper on the archive a couple of weeks ago, where they show that now if you don't assume that you have a perfect quantum computer, but you really try to compile using error correction your algorithm, and you find that, for instance, for factoring the 10,000 perfect qubits that you need and now translate to a few tens of millions of physical qubits. And this exercise had been done before, and I mean, all of the people who really try to put realistic hardware assumption and then compile will find that you need millions of qubits. Okay, so now I'll try to give you a bit of our angle. How do we think we can try and make this problem easier? So the idea, I mentioned it before, is really to try and find a new technology, build a new technology that's fundamentally good for error correction, such that our way, I mean, our path to universal quantum computer is really to first build these better qubits and then only start scaling, as opposed to current approaches where you start both to scale and to increase the qubit quality, for instance, what IBM presented, or increase the number of qubits. And the idea here is to rely on bosonic error correction. So when I show you the surface code and the array, I started by saying, okay, the core idea behind error correction is that errors are typically local, and so we need to find some delocalization of the encoded information to have protection. The idea of bosonic error correction is to do that, but in a space in which you have only one physical quantum system. So more precisely, the idea is to encode quantum information into a harmonic oscillator. So harmonic oscillator, the classical analog would be just a pendulum. It's a single object, but it gives you access to an infinite Hilbert space in which you can somehow delocalize information. And then the typical choice of encoding that you have in this space to delocalize information is referred to as the bosonic qubit. So there are a whole family of different qubits. The two popular of them, I mean, two of them that have been demonstrated in the lab being the GKP qubits on the left, where you use grid states in phase space, and the other one being the cat states that we build at Alice and Bob. So why does it help fundamentally? So I will try and explain that. The idea behind the cat qubit is that here you have on the right Wigner representation of the quantum state of light, and basically the two computational states that we use, 0 and 1, can be represented as blobs in phase space. And as we increase the number of photons in these states, they get further and further away in phase space. So somehow they get delocalized. And the reason why this provides protection is really because if you look at the natural errors occurring on the harmonic oscillator, then it will give you local diffusion in phase space. So there is a barrier of potential, and as you increase the distance between these two states, then the probability that environment can induce a jump between these two states is exponentially suppressed with the average number of photons. Now the price that you pay is that if you look at the errors in the other quadratures, they increase linearly, but the difference of scaling between these two errors is really where we have an advantage. So this was typically demonstrated in a lab a couple of years ago, where here you have as an x-axis the number of photons that you put in the cat state, and as a y-axis the bit flip lifetime of your qubit in a log scale. So here you really have an exponential increase of bit flip time up until a point where it saturates, and this saturation you can understand it as this is really the rate where you have non-local phenomena in your lab. So basically, as long as your errors are local in phase space, then increasing the size of the cat qubit results in this nice exponential scaling, and then at some point you have a physical phenomena that induces transitions here at a rate 1 millisecond, and then it starts to saturate. So in this specific experiment 2 years ago, the saturation was just due to the tomographic apparatus that it used to measure the cat qubit. So they removed it. And that's a more recent paper where they were now able to observe an exponential suppression of bit flips over 8 orders of magnitude up to a point of about 100 seconds. So here again there is a saturation, meaning that you have another non-local phenomena inducing bit flips, and in this case it can either be due to high energy particles or to slow drifts in the experiment, but this is something that we're investigating right now. And since this first experiment, there have been other experiments at Yale University and also in the AWS team that relies on cat qubits, demonstrating this nice exponential suppression of bit flips. So now with this background, I want to motivate a bit, why do I call this hardware efficient? Again, so assume you were starting with a qubit that has as many bit flips as phase flips, and you were embedding this qubit into a repetition code against bit flips. Then what you will find is that the probability of having a logical bit flip, which is the probability that the majority of the qubit flips, decreases exponentially with the distance of the code, provided that you are below the threshold. And so somehow this is really the same kind of scaling that we have with a cat qubit, but now instead of having to rely on many physical qubits on a chip, what plays the role of the code distance is just the number of photons that you put in the cat qubit. So it's just somehow the microwave power that you put. So there were 2 experiments that you can put in regard, I mean, with this context. There is the one where you really have a single cat qubit and you look at the exponential suppression of bit flips. And the other one where the Google experiment where they built a repetition code using different transmons. And in both cases, you can see this exponential suppression of the logical error with the code distance or the photon number. But the big difference is that in the case of cat qubit, you still have only one physical quantum element on the chip. Whereas when you do rely on a transmon or regular 2-level systems, you have to increase the number of qubits, hence the complexity of the machine. So far I've only shown, trying to give you a taste of the philosophy behind the bosonic qubits that we build at Alice & Bob, but that other companies like AWS or North Quantic are also relying on, and trying to motivate the reason why this should give access to better qubits without inducing too much overhead. So one question that you could have is, does it translate to an advantage at scale? Following this approach, do you really decrease the size of the machine ultimately that you'll have to beat? So that's what I want to discuss in the last couple of minutes. And I want to flash some results that are not published yet, that will be in the press in a couple of days, where we've done the exercise of compiling Shor's algorithm on our architecture. So really, it's based on a fine-grained description of a processor made of cat qubits, so an array of qubits where you specify circuit-level noise and take into account all sources of imperfections into the chip, and then do the effort of compiling the algorithm on the fully fault-tolerant architecture. And what we find, for instance, is that you can compute discrete logarithm on elliptic curves in about 12 hours and with about 100,000 cat qubits. So you might, the reason why we chose this specific example is because elliptic curve cryptography is easier to attack given that the classical algorithms are less efficient, so these people use a shorter key size. But for a quantum computer, it actually makes no difference. We've still done the exercise of looking at short algorithms, so to try and give you a bit of a comparison. And here you can see on the left-hand side, as a function of the size of the integer that you're trying to factorize, the number of qubits, of cat qubits that you need on the left and the time it takes on the right. And basically what we find is that with our architecture, you can factorize 2048-bit integers with a few 100,000 cat qubits, so 300,000 cat qubits in a couple of days. So you might be tempted to compare that to the figures I've shown you earlier, saying that with the surface code and transmon, you did about 8 hours and 20 million noisy qubits. I still want to warn you that these direct comparisons are somehow tricky to make, because these numbers highly rely on the assumptions you've made about the hardware, about the level of noises. And when you have different architectures, it's hard to say whether the assumptions that you've made are equally realistic. My point is that, for instance, in the case of transmons, if you decrease the physical error rate, then you will also decrease by a lot the final number of qubits that you need to run Shor. So it brings me to my take-home messages. I hope to have convinced you that many applications at scale require quantum error correction, so it's not enough to just have an efficient quantum algorithm that solves a specific problem. What you want to be looking at the end of the day is really what is the size, the instance of that problem that you want to solve to have a business advantage. And also that resource estimation is very important, because there might be problems for which you know that there is an exponential speed up, so you're like, okay, this will be within the reach of quantum computers, but actually doing the math, you find that you need millions of qubits, which says that it won't be practical before an important number of years. Another thing I want to stress is the metrics that are important to follow the development of the hardware. I think that for a NISQ processor, there are a lot of different metrics like the quantum volume or the Q-score that capture gate fidelities, connectivity, and everything you would want at the end of the day to know exactly what is the depth that you can execute. For fault-tolerant quantum computation, it's not so clear that this is the right metric. So there are some architectures for which there is a kind of direct correspondence between the quantum volume, for instance, and the fault-tolerant error threshold. But there are other architectures, like, for instance, the cat qubits, where it does not translate so easily, because you have other things that enter into play, like the noise bias, for instance, that are not at all captured by these metrics. So in terms of performing fully fault-tolerant quantum computation, I think the relevant metrics are rather where you are with the threshold of your architecture. So are you able to execute your code at the threshold where increasing the distance of the code decreases the logical error rate, like Google is doing right now? And eventually, you don't want to be at threshold, but you want to be at least one order of magnitude below that to get a nice exponential scaling and hence decrease the number of resources. And another way of looking at it is the so-called tera-QUB footprint. So tera-QUB stands for a tera number of quantum operations, so 10 to the 12 quantum operation. And so basically, the tera-QUB footprint refers to the number of physical qubits you need to have for a given logical qubit to achieve a logical error rate of 10 to the minus 12. Because the threshold is important because it sets basically the quality of the hardware that needs to be achieved in the lab so that error correction will start working. But the tera-QUB footprint is really what tells you what is the size of the machine that you will need. Basically, what is the overhead of physical qubit per logical qubit that you will need to run applications. So I think I've went through all of my messages, and I will be happy to take some questions.
Very quickly, please.
Do you have an opinion on how useful cat qubits will be in the nearer term sort of regime before we get to this, many millions of
I do have an opinion on that. So cat qubits are not as recent as other superconducting qubits, so they're harder to stabilize, for instance. And if you look in the literature, they are much more recent. So meaning there are not that many gates available, and the gate fidelities might not be so high. So in my opinion, it's really a technology that's meant for error correction, in the sense that this price that you pay at the physical level by building these more complex objects is really targeted at the end of the day having less qubit per logical qubit. But if you ask me, I don't think there would be good qubits for NISQ applications. And there is one very easy way to understand it is that, there is a noise bias that's quite important. So it's nice for error correction because you only have to correct for one type of error. But if you could find NISQ algorithms that were working well on these qubits, then these algorithms would somehow be almost classical. Because it would mean it's typically an algorithm that is susceptible to only one type of noise. So it's an active field of research, actually. But so far, I don't think there is I don't think it's very promising.